Alrighty, hello and welcome to excuse me, our Wednesday lecture. Today we're gonna be wrapping up chapter chapter 8, starting chapter 9, and yeah, it'll be a good day. Before we dive in, I wanted to spend a minute and talk about exam 3. So first off, they it closed. I got a chance to look at it, and I was actually shocked by how low the average was. That being said, when I went in and I looked at it, there were a few exams that were clearly outliers. That, like, their exams where people started them and the scores were so low that they were outliers. So when you look at Canvas as a student, you see the absolute average of every score for every attempt on the exam, but there were some that were just, that, like I said, are outliers. So and Canvas doesn't have any way of knowing that or showing that. So after the outliers were removed from the data set, the average for exam 3 came out to be a 60%, which is still on the low side, but it's not unusual for what I typically see on this exam. This one usually has the lowest average of all the exams that I give. Part of the reason for that is on this exam, you get a full metal taste of a variety of topics that not only are challenging in and of themselves, but in addition, like all of the thermochemistry stuff, the Hess's Law stuff, work, all that business, isn't really covered in Chem 305. So in addition to the material being challenging in and of itself, this is your first moment where general chemistry kind of distinguishes itself from your introductory course, and so it tends to be an exam where a lot of students struggle more so than the others. So again, 60% is a low average, but it's not abnormally low. So I just kind of wanted to give you a sense of where things actually stood, because the average that Canvas displayed isn't accurate when you take into account the outliers. That being said, one takeaway is the worst is more or less over, because the exam 4 usually has a higher average than the third. So anyways, I just wanted to give you that update. Also, thank you to everybody who asked about typos. I'm currently going through the exam, checking for typos. When they're identified, I'll not only fix them, but everybody who drew a flawed problem out of the problem bank will get full credit. So I'm in the process of analyzing that, and there'll be more on that to come in the future. All right. With that being said, let's go ahead and dive into some new material. So we said on Monday that we have 2 things left to cover as far as electron configurations are concerned, and those 2 things are we have to talk about ions, and we have to talk about anomalies. There are some anomalies that we have to talk about on the periodic table. All right. So let's start by talking about electron configurations for ions. Here, hang on one second. My brother's on the phone in the next room, and I'm picking him up on my microphone. Hang on one sec. All right. Oh, am I all blurry? There we go. Okay. Back in focus. Okay, so let's talk about the electron configurations and orbital diagrams for ions. Now, the main difference between an ion and an element, as you know, is that elements are net neutral, right? The number of electrons are equal to the number of protons in the atom, whereas ions have an imbalance, all right? So ions have either gained or lost electrons to be positively charged or negatively charged. So if you were asked to write, for example, the electron configuration and orbital diagram for the oxide ion, right? Oxygen with a -2 charge, the way you do this is first you have to write the electron configuration for just oxygen, the atom, and then once you have, you adjust the number of electrons either up or down depending upon whether your charge is negative or positive. So it starts by writing the electron configuration for just oxygen, whose nearest noble gas with fewer electrons is helium. So oxygen, the electron configuration for oxygen, we'll start with helium in a bracket. All right, next we identify the period oxygen's on. It is on the second period. All right, and oxygen is in the p block, which means that we will have electrons in the 2p subshell. Next, we need to count our way over. First, starting again at the very left of the periodic table, we bounce 1, 2 spaces in, so this will be 2s2, and then we jump over to the p block. This will be 2p, 1, 2, 3, 4. So the electron configuration for oxygen, the atom, is 2s2, 2p4. All right. Now, when it comes to the oxide anion, has a charge of -2, which means there are 2 extra electrons. All right, 2 extra electrons. That means that we need to add 2 electrons to our electron configuration for oxygen. So for oxide, the anion, we're still going to have that helium core. We're still going to have 2s2. But now, where oxygen, the neutral atom, has 4p electrons, we have 2 additional. So this will be 2p6. And this is the electron configuration for the oxide anion. Now the orbital diagram, once you have the electron configuration for oxide, you can write the orbital diagram. It'll have our electrons in the 2s subshell as well as the 2p. Right, and so this will be 2 electrons in the 2s and 1, 2, 3, 4, 5, and 6 electrons in the 2p. All right, that is how you handle an anion. You add the extra electrons to the neutral electron configuration, and then from that electron configuration for the anion, you write the orbital diagram. All right, so that is that's how you handle an anion. Let's do an example with a cation. Let's do magnesium 2+. All right, first we begin with writing the electron configuration for magnesium. Its nearest noble gas with fewer electrons is neon. All right. Magnesium is on the third period. It is in the S block, and it is 1, 2 spaces in to the S block. All right. Now, with a cation, with the anion example that I just did, all we had to do was add 2 electrons. All right. the cation, writing a electron configuration and orbital diagram for a cation has slightly more detail to it. There's one additional piece of information. Once you write the electron configuration for the neutral atom, as you move to the cation, you need to remember this. You always remove electrons from the highest energy shell first. All right? Always remove electrons from the highest energy shell first. Now, with magnesium, that highest energy shell is the 3s shell. We need to lose 2 electrons. So you could say that magnesium 2+ has an electron configuration of just neon. Or, so that, and which is acceptable. You could say it's just all the electrons for neon. Or, if you want, you could write out the electron configuration for neon, which is helium 3s2, 3p6. Both of these are acceptable as electron configurations, but only, even if you don't write out the electron configuration for neon, you still need to know what it looks like, because to do the orbital diagram for magnesium, you need to know that you have, oh sorry, I messed this up. Neon is not 3s, 3p, it's 2s, 2p. Oops. The orbital diagram for magnesium 2+ has electrons in the 2s and 2p subshells. Oh, that's a funky looking thing. There we go. All right, so all right, so this is the electron configuration and orbital diagram for magnesium 2+. All right, let's get a few more examples under our belt. All right, what about, let's do the orbital diagram and electron configuration for palladium 2. All right. First step is we need to write the electron configuration for the neutral palladium atom. All right. Then once we have that in hand, we'll remove 2 electrons from its highest energy shell. All right. So palladium's nearest noble gas with fewer electrons is krypton, Kr. Palladium is on the 5th period. So we know we're going to be putting electrons into the 5s subshell. But remember that once you cross from the s block into the d block, you have to drop down a level. Excuse me, so it goes from 5s to 4d. This will be 5s2, 4d, and let's see. So we go 5s1, 2, 4d, 1, 2, 3, 4, 5, 6, 7, 8. 4d, 8. All right? That is for neutral palladium. Now, to get to our ion, we need to, since it has a positive 2 charge, we know we've lost 2 electrons, so we need to remove 2 electrons from the highest energy shell, which for palladium is n equals 5. So we're going to lose 2 electrons out of the s subshell. Kate, that is a great question. So Kate just asked how many valence electrons does neutral palladium have? And the answer to that question is everything you see outside the noble gas configuration. So we've got 10 total valence electrons for neutral palladium. But once we remove 2 from our highest energy subshell, highest energy shell, we get palladium, or the electron configuration for palladium 2 will just be krypton 4d8, because it lost 2 electrons out of its highest energy shell. So that will be the electron configuration, and the orbital diagram will only have 8 electrons in the 4d subshell. Alright, so this is the electron configuration and orbital diagram for palladium. Alright, let's do another example. Let's do the electron configuration and orbital diagram for thorium 3. Alright, thorium with a positive 3 charge. Alright, so we've got to first locate thorium. It is number 90, which means its nearest noble gas is radon, right? Because, again, you begin writing the electron configuration for an ion by first writing the electron configuration for the neutral atom, and then you adjust electrons either up or down. So we're going to start with radon. All right, now we have to remember where thorium comes in. Thorium is in the second row of the F block, which means it enters right here after actinium, all right, which places it on the 7th period. So we're going to have 7s. Let's not forget, we got to cross into the D block. So we go 6D. So we're transitioning from 7s to 6D down to 5F when we make that jump into the F block. So 7s, 6D, 5F. Now let's count our way through. We go 2 spaces into the S block, 1 space into the D block, and next we jump down into the F block, and we're only 1 space into the F block. So the electron configuration for thorium is radon 7s 6d 1 7s2 6d1 5f 1. All right, that is the electron configuration for the neutral atom. Now we need to remove we need to remove 3 electrons from the highest energy shells, right? But the thing is, we actually only have 2 electrons in our highest energy shell. So that means the third one is going to have to come from our 6D, all right? That will be our 2 electrons plus 1 electron is 3 electrons. So after we remove the electrons to form the ion, those electrons will come from the 7s followed by the 1d subshell. So you need to, there we go. Just make that a little clearer. So the electron configuration for thorium 3 then will just be radon in brackets followed by 5 because it's lost its 2s electrons and its 1d electron. So the orbital diagram will just be our 5f subshell, which has 7 orbitals in it, and 1 lonely electron hanging out. All right. So that is how you handle ions. You always remove from the highest shell first. If you run out and you still got to take some out, you just keep moving down the shells. All right, now that was those were ions. We have one last thing to cover, and then you'll be able to handle any and all electron configurations. We need to talk about some anomalies. So let's go ahead and write the electron configuration for chromium. All right, let's write the electron configuration for chromium. I've been dodging this one on purpose. So first, we got to find chromium. Its nearest noble gas with fewer electrons is argon. All right, and now we got to find the period it lies on. It is on the 4th period, and it is going to involve the crossover from the S block to the D block. So we remember that we drop an energy level when we cross from S to D. So we're going to have 4 S electrons and 3 D electrons. And when you count your way through, we go 2 spaces into the S block. So that's 4s2, followed by 1, 2, 3, 4 spaces in to the D block. All right. Now here's the thing. As written, this electron configuration is incorrect. All right, this electron configuration is incorrect, but it'll take looking at the orbital diagram to understand what's wrong with this one. All right? So let's look at the orbital diagram. So it'll have, we have our 4s subshell and our 3d subshell. And if we look at the electrons present, we have 2 electrons in our 4s subshell, and then 1, 2, 3, 4 electrons in our 3d subshell. Okay, now let's pause for a minute and think about what the direction of these arrows mean. All right, what do the directions of these arrows mean? Well, they represent the spin quantum number. You'll remember from chapter 7 that the ms, the spin quantum number, can be either positive 1/2 or negative 1/2, and that is to show the direction or the orientation of the magnetic field, right? Kind of like a North Pole, South Pole kind of thing. All right, now, turns out something very special happens when you have 4 parallel spins lined up in the D block. All right? Whenever there are 4 I should say 4 electrons with parallel spins in, I should say, in a D subshell. This, and that's important, this does not happen for P subshells, it does not happen for F subshells. This is unique to the D subshell. When you have four electrons with parallel spins in a D subshell, the magnetic field of these things build, all right, because they're all in parallel. So they're adding together, they're growing stronger, and they're strong enough when you have four in a row to steal an electron from an S subshell and promote it up into the D subshell, so that you get 5 parallel spins together. So whenever there are 4 electrons with parallel spins in a D subshell, one available electron is promoted from the S subshell. All right, the strength of the magnetic field of these 4 electrons in parallel is enough to steal one of the 2 electrons in the S subshell and promote it up until the D subshell. So the orbital diagram for chromium is actually like this. There's actually 1 electron in the S subshell, and then 1, 2, 3, 4, 5 electrons in the D subshell. This is the actual orbital diagram for chromium, which means that the electron configuration for chromium is actually argon, in brackets, 4s1 3d5. All right, as we said before, the one that you wrote out normally is incorrect, because you have those 4 electrons in parallel. They steal one from the S subshell, and so the correct configuration is argon 4s1 3d5. And this happens every time you have 4 electrons with parallel spins in the D block. All right? Let's do another example to kind of solidify this. Let's write the electron configuration for silver. All right, so let's start. Silver is here, number 47. Krypton is its nearest noble gas with fewer electrons, so we throw krypton in a bracket. Next, we identify the period that we're on, and we are on the 5th period for silver. Kate, great question. It will only steal from the S subshell. All right, so we're dealing with the 5th period, which means we'll have electrons in the 5s. Totally. And we'll be crossing over into the 4d. right? So we move 1, 2 spaces through the S block, and then we move 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces in to the D block. All right? And just like before, this electron configuration for silver is incorrect. And we'll take a look at the orbital diagram to understand why. So we have the 5s subshell, the 4d subshell. We have 1, 2 electrons in the 5s, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons in the 4d. Now, this one's a little harder to see, which is why I've added color. You'll remember that in the previous example I said anytime you have 4 electrons with parallel spin, the magnetic strength of those spins adding together will be strong enough for them to steal an electron, promote an electron from the S up into the D. And that is exactly what happens right here. And you can see that we have 1, 2, 3, 4 electrons with parallel spins. In this case, they're pointing down, but they're still all parallel. So they're going to steal 1 electron from the S subshell and promote it up into the D subshell. So actually, the orbital diagram for silver looks like this. It's 5s1, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Well, I'll keep it blue actually. 10. There's that electron that's promoted up. And so the actual electron configuration then will be krypton in a bracket, 5s1, 4d, 10. All right, that is the electron configuration for silver. All right, here's the thing. So how I do these is I write out the electron configuration like normal. I write the orbital diagram, and then if I notice, wait, I've got 4 parallel spins, I promote one, then I go back and fix my orbital diagram. For those of you who like to keep an eye out and watch, kind of catch it before you have to do all that business, here's the thing to look for. If you have a 4 electrons in the d orbital or 9. Those are the 2 instances. If you got d4 or d9, then you promote 1 electron from the S subshell if it's available. All right. If it's available, you promote 1 electron from the S subshell. So I'm going to do 2 examples now, one where we will and one where we won't because there's no electron available. So let's do let's do this one. Let's do tungsten. Oops, nope. Tungsten. Tungsten, if you're wondering why a element whose name starts with T has a W, it has a W as a symbol because of its medieval name. Tungsten was called wolfram. It's one of the hardest elements that we know of, one of the hardest metals that we know of. And it was called Wolfram because this is what they used to kill werewolves with back in the day. Back in the Middle Ages is when it was named. You'd use it for slaying werewolves. And fun fact, it's what my wedding ring is made of tungsten. And I did that by design, just in case I ever come up against a werewolf. All I have to do is punch it in the face, and it will shatter, which would be pretty awesome. I can't wait for that day. Anyways, let's do the electron configuration for Wolfram. We're going to start with a xenon core. Right now, let's look at the period we're on. All right, and we are on the 6th period. All right, so we're dealing with 6s. We're going to be crossing over into the 5d. But you'll notice that we said every element that comes after lanthanum or actinum will have a full F block. So we actually do have a 4F14 situation going on. All right. Now let's count our electrons. We go 2 spaces into the S block, so 6s, 2. And then we go 1, 2, 3, 4 spaces in, 5d, 4. And this right here is the giveaway. We have 4 parallel spins, so we need to promote 1 electron from the 6s orbital. So you can correct it right now if you want, if you're that type of person. We can do the electron configuration will be xenon 6s 1 5d 5 4f 14. All right. Oh, let me keep my coloring scheme consistent. For F, oops, 14. So our orbital diagram will look like this. We've got our 6s subshell, our 5d subshell, and our 4f subshell. We have 14 electrons in our 4f subshell. We have 1 electron in our 6s subshell, and we have 5 electrons in our 5d subshell. She went with platinum, so she's not equipped to slay any demonic or evil creatures. Yeah. So she didn't. But when I saw that Wolfram was an option, because I was like researching metals that could be used in different rings, I was like, that's the one. And I've been ready and waiting ever since. All right, so this is an example of catching it early. You see that D4, and you know instantly that we're going to promote 1 from the S subshell. Now I want to give you an example where you could run into a D4 or a D9 and not be able to promote it. All right, so it's not an automatic thing, as you'll see in the following example. Let's do copper 2. Actually not. Tungsten carbide, as you can see, is black, and platinum is a very, very shiny, silvery metal, and it's just got this very, very kind of like light silvery color to it. So at least it could scare a vampire, right? Vampires can't touch silver. Werewolves actually can't either. But even though it's platinum, it might be enough to give them some pause. So at least it has some defensive value. So we're going to start by writing the electron configuration for copper. All right. Copper's nearest noble gas is argon. So we're going to start by putting argon in brackets. Next, we identify the period we're sitting on. We are on the 4th period. Let's see, 4s. And then we're going to be crossing into the 3d. Sammy, real quick before I continue with this problem. Oh my gosh, sorry. Emma, that is so cool. I did not know that piece of lore. That is awesome. Sammy, I had one other student contact me about like a missing exam, and the student had taken the exam, but it wasn't showing up on Canvas. It just said like the little bar. It wasn't like a 0, like you scored 0 points, but just a bar, like no score. And for I don't know why it happened, but it did happen to one other student. I was able to go into Canvas because it had recorded it. It was just kind of like buried deep and wasn't registered. So if you're not seeing any result or a missing exam, shoot me an email as a reminder so I'll remember to go back and look and find it, because it's probably there just like it was for this other student. It took a while to like find it, but now I know where to go, so I'll be able to solve that problem for you. I just will need an email reminder, because without that, I know I'll forget. But I'll do some digging and we'll be able to get to the bottom of it. Okay, and I wanted to say that before we continued with this example. So with copper, we're going to be crossing over from the 4s subshell into the 3d subshell. Move 2 spaces in, so we've got 4s2. Then we go 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d, 9. Now, you'll notice... Yeah, totally. All right, you'll notice that we're dealing with that 9. So you may go, okay, I know I'm going to promote 1 electron from my highest energy, from the S subshell, right? So this will be 4s1, 3d, it'll bump it up to 3d10, right? Which there's 5d orbitals holding 2 electrons each. 3d10, totally a possibility. So this is, by the way, the electron configuration for copper, right? For neutral copper. But we're dealing with an ion, so we got to remember that we got to lose 2 electrons. The first one, it's always got to come out of our highest energy shell, right? We're going to lose 1 electron from here, plus we're going to lose another electron from here. So this will actually bump things back down, the electron configuration for copper, 2 ions will be argon in a bracket. And then our 4s subshell has no electrons left in it, so it won't have any electrons. You can write 4s0, but you don't typically do that. It's not explicitly wrong, however, and then our 3d subshell drops to 9. And so this is one instance where you do end up with 9 electrons in your d subshell, but the reason why you end up with 9 is because you've lost electrons to get there. There are no more electrons in the s subshell to promote up. So this is the electron configuration and orbital diagram for copper 2+. All right, the promotion still happens. That's the and so you see for neutral copper, it's argon 4s1 3d10. But then when you do 2+, you got to lose 2 electrons, so you bump back down to 9. So I don't. The reason why I'm doing this example is I don't want you to think that having 9 electrons in your d orbitals or 4 electrons in your d orbitals is always wrong. It can happen, but it only happens when there are no electrons in your s subshell that you can promote. If that happens, you let it ride. Okay. All right, now at this moment in time, you can handle any electron configuration I can throw at you. All right, so you at this point have the knowledge to do that. The last topic in chapter 8 that we have to go over is the topic of periodic trends. All right, periodic trends. And actually, I don't know why I made my periodic table disappear. Because I need it. I'm actually going to slightly reposition it. Okay. So, periodic trends is a general kind of overarching category that there are certain properties of elements that change and form a trend as you move throughout the periodic table, right? Moving right to left, some of these properties get more pronounced, get stronger or weaker as you move top to bottom, bottom to top. The properties change in a regular, predictable fashion, and so that's why they're called trends across the periodic table. And we're going to look at a handful of them right now. The first periodic trend is atomic radius. All right, and the atomic radius is defined as the distance between the nucleus of an atom and the distance between the nucleus and the valence electrons. All right, so the highest energy shell. All right, and we know that the higher and higher in energy corresponds to further distance from the nucleus, right? So basically the take home here is a larger N means that you will have a larger size for your atom. Atomic radius is essentially a measure of the size of an atom. If you assume that it's more or less spherical, the larger your radius is, the bigger your your atom will be. All right? So it should come as no surprise then that the way this trends across the periodic table is as you move from the top of the periodic table to the bottom, the atomic size, atomic radius increases. The lower down on the periodic table you are, the bigger you are. All right? So if I asked you to actually, sorry, hang on. Need to hide this a little bit better. You'll see why in a minute. So the smallest stuff are going to be closest to the top. The largest stuff will be closest to the bottom. So, so if I asked you which atom was larger, is oxygen versus tellurium, right? Oxygen is here on the second period, tellurium is here on the fifth period. Tellurium is larger because its valence electrons are in the fifth shell, whereas oxygen's valence electrons are in the second shell. All right? And that will always be the case. Whichever element is lower on the periodic table will be the larger atom. All right? Where things get a little trickier is as you move across the periodic table, as you move from the right to the left. All right? As you move from that, now this one can be a little confusing for students. It's very common for students to mess this up because, for example, if you compare sodium, for example, to chlorine, which one will be larger? And what makes this tricky is you'll notice 1, 2, 3, they're both on the same period. So in the example of sodium versus, not fluorine, chlorine, they both have the same shell. Their valence electrons are on the same shell. So we can't say, oh, one has a larger principal quantum number, so it's a bigger atom. How does it trend as you move from the left to the right? And the way it trends is it actually gets smaller as you move from left to right, which might be counterintuitive. Because it's one thing, I know when I was a student, I looked at these two and I was like, well, chlorine has 17 electrons and sodium has 11. So I would think that chlorine is larger. And it's not, all right? It's not. Here's the deal, all right? When you compare these two, so sodium has 11 protons in its nucleus, and chlorine has 17 protons in its nucleus. All right. Now, all the electrons out in the third shell, right, n equals 3, are attracted, right, they feel the pull of each nucleus. I'm just going to scoot chlorine over. Alright, this is n equals 3. They're out on the third shell. The thing is, there is a greater attraction between the valence electrons for chlorine and its nucleus because there are more protons in that nucleus. They're roughly the same distance from the nucleus as the valence electrons for sodium, but because there's more electrons in that nucleus, the pull is harder. So the electrons for chlorine shrink slightly relative to the electrons for sodium, which are able to breathe a little more because that force isn't pulling quite so hard. So as you move across a period from the left side to the right side, your atomic size, your atomic radius gets smaller. So because sodium is further to the left, sodium is larger. It's the larger of these two. All right. Now you only use this argument as a tiebreaker when you have two elements that are on the same period. Then whichever one is further to the left is larger. If they're not on the same period, you always go down. You go with the one that's lower down on the periodic table. That one will always be bigger. If they're the same period, then whichever one is further to the left will be larger. All right, and that is the periodic trend for atomic radius. A periodic trend that we've talked about already, but we should take a moment to just review it for completeness. Electronegativity. Electronegativity trends on the periodic table, and remember this is electronegativity is a measure of, I'm going to put this in quotes, how bad, unquote, an atom wants to gain electrons. All right, and electronegativity trends across the periodic table as you move from left to right. The electronegativity of atoms increase, and as you move from the bottom to the top, the electronegativity of atoms also increase. So the most electronegative elements are up in the top right, and the least electronegative elements are down in the bottom left-hand corner. So for all of these examples, let's determine the most electronegative. All right, determine the most electronegative. So, let's do some examples. Let's go for oxygen versus boron. All right, in oxygen versus boron, they're both on the same row, but we know whichever one is further to the right is more electronegative, so oxygen wins out. More electronegative than boron. What about oxygen versus bromine? Or, hang on. Let's do a different one. We're gonna do chlorine versus nitrogen. All right, let's take a look here. So we've got chlorine here, nitrogen here. Now, here, this one's not as straightforward because Nitrogen is higher than chlorine, but chlorine is further to the right than nitrogen. So how do you figure this out? Well, nitrogen is one space higher than chlorine, but chlorine is two spaces further to the right than nitrogen. So chlorine is more electronegative because it's two spaces over to nitrogen's one space up. All right? The real question comes in, what do you do in a situation like chlorine versus oxygen? All right? This is the real puzzle because oxygen is one space higher, chlorine is one space to the right. Which one wins in that situation? It's not a pure tie. When you have one that's one space higher, the other element that's one space further to the right, in that instance, you take the higher one. All right? Whichever one's higher in that case will win out. If it's a different distance, if one is two further to the right, that one will be more electronegative. But when it's 1-to-1, the higher one wins the tie. All right? And that is electronegativity. All right, let's take a look at ionization energy. All right, ionization energy is the energy required to remove an electron from an atom. All right? The energy required to remove an electron from an atom. So we're literally talking about a reaction where you have a neutral element losing an electron. So the element will become a cation and it will lose one electron in this process. Now, think about this. Is it going to take more energy or less energy to remove an electron from a very electronegative element, right? We were just talking about electronegativity. And electronegativity is how bad an element wants an electron. So if you have a high electronegativity, it's going to take a lot of energy to steal an electron away from that element because it doesn't want to lose electrons, it wants to gain them. If you have a low electronegativity, it's not going to take a lot of energy to steal that electron away because that element really doesn't care. So this periodic trend, ionization energy, tracks with electronegativity. The amount of energy it takes to steal an electron from an element increases as you move from left to right, and it increases as you move from top to bottom. All right? This one tracks with electronegativity. Let's take a look at one more periodic trend. Let's look at something called electron affinity. So let's take a look at electron affinity. There we go. So with electron affinity, we're talking about a very similar reaction. It's kind of like the opposite process of ionization energy. With ionization energy, your element was losing an electron. For electron affinity, we're talking about a neutral element gaining an electron to become an anion. Well, now when you think about it, what elements on the periodic table want to become anions? The electronegative ones. So the largest electron affinities can be found where you have the largest electronegativities. And the smallest electron affinities can be found where you have the smallest electronegativity. So electron affinity and ionization energy track perfectly with electronegativity. It's the atomic radius one that's kind of off. It's kind of different than the rest. All right. Now that brings us to the end of chapter 8. All right. Now we're moving into chapter 9. And I'm just going to give a very kind of brief introduction to chapter 9. We got like 14 minutes left in lecture, so we're not going to get too deep into the weeds today, but we'll pick this up on Monday with chapter 9. So chapter 9 is the natural extension of our journey exploring kind of the electronic structure of atoms, right? This started in chapter 7, where we were first looking at the individual wave functions for individual electrons orbiting a nucleus, right? Then we took a step back in chapter 8 and said, okay, we're going to look at entire atoms, all the electrons around an entire atom, and that led us to a discussion of orbital diagrams and electron configurations. Well, in chapter 9, we take the next jump. We move into an even larger scale. We're going to start talking about all of the electrons in molecules. So we went from electrons to atoms, individual electrons to atoms, and now we're making the jump to molecules. So we keep getting larger and larger in scale. All right. So this is going to be our introduction to electronic structure, the electronic structure of whole molecules, and that has to begin with a discussion of Lewis theory. Lewis theory. Okay. What is this Lewis theory thing? It starts with Lewis theory is simply a different way of depicting something we already know. All right? It's a different way of looking at structure. So, for example, if you have a nitrogen atom, all right, we could write out the electron configuration, right? Nitrogen uses helium for its noble gas abbreviation, and then when you use the periodic table, you see that it's 2s2, 2p, 3. All right, that's the electron configuration. We could write the orbital diagram. Right, for this compound. And in the orbital diagram, we're just looking at the valence electrons, right? So the orbital diagram here has the 2s and 2p subshells. And we have 2 electrons in our 2s orbital and 1, 2, 3 electrons in our 2p subshell. All right. Now, the Lewis, it's called the Lewis dot structure, is a way of depicting atomic structure. And we're starting with atomic. We're going to move to molecular, but we're starting with atomic. The Lewis dot structure for an atom also only focuses on valence electrons, just like the orbital diagram. All right? Emma, great question. Emma, so Emma's question was for orbital diagrams. Is it wrong if you write it out entirely, including heliums? It's totally not wrong. That is 100% correct to do it this way. However, I think it's actually, well, one, easier. It's a little faster if you just write the valence electrons, especially when the atoms get much larger. When you're juggling like 89 electrons, it'll take a lot of space to write that all out. But also, it makes it easier to then write the Lewis dot structures if you're using the noble gas abbreviation, because the Lewis dot structure only uses the valence electrons. So you can write an orbital diagram out using everything, but if you restrict it to valence, it makes it easier to transition to the Lewis dot. All right, now, so here's the Lewis dot structure. The way the Lewis dot structure depicts an atom with its valence electrons is you write the elemental symbol, and then the electrons are depicted as dots around that symbol, and you kind of envision it. You kind of look at the atom as having four sides. So you kind of look at it as if it were in a box. I'm going to, I'm going to write that out. So we kind of have four sides going on, and then you depict the electrons as individual dots. So we have 5 valence electrons, right? Because we have 2 in the S plus 3 in the P. So we have 5 electrons. And you start by putting 1 dot on one side, then you move to the next side, 2, 3, 4, and then 5. Each side of your Lewis dot structure low-key represents an orbital, right? Because you'll notice you have 1, 2, 3, 4 orbitals for the holding the valence electron. So each side of the elemental symbol in that kind of like box situation, there, maybe like that might be better, represents an orbital in the orbital diagram electron configuration, and then each dot represents an electron. You'll never have more than 2 dots on one side, because you never have more than 2 electrons in one orbital. All right, so this would be the Lewis dot structure for nitrogen. If we wanted to compare, for example, magnesium, the noble gas abbreviation for magnesium, again, would be helium, and then it's just simply 2s2. So the orbital diagram, let's not do, magnesium, let's do sodium. Going off my notes for a moment here. Two S1. So we have 1 electron here. And so the electron configuration the Lewis dot structure for sodium would be just 1 dot. well, and it doesn't matter which side you put it on, as long as there's only one valence electron around your central atom. Let's do neon. Neon also has a noble gas abbreviation of helium. So this is 2s2. Oh, magnesium. Sorry. My bad. Has neon as the noble gas abbreviation. No, that was totally my bad. I'll still do the Lewis dot structure for neon though. So we have our 2s subshell, our 2p subshell, and then we'll have 2 electrons in our 2s and 1, 2, 3, 4, 5, and 6 electrons in our 2p. So our Lewis dot structure for neon will be, oh sorry, hang on, let me do this properly. We've got 8 electrons to place, so we go 1, 2, 3, 4, 5, 6, 7, 8. So that would be the Lewis dot structure for neon. Now, when it comes to drawing Lewis dot structures, you may be wondering, do I have to write out the electron configuration orbital diagram for them each time? And the answer is no. There's actually a quick way to draw these out based on their position on the periodic table. All right. So something you should know, and in the spirit of full disclosure, I want to say this up front. Lewis theory applies to main group elements. All right. Lewis theory does not do a good job of predicting the structure or reactivity for transition metal elements. And so a new theory had to be developed called molecular orbital theory. We'll get to that a little bit later. But Lewis theory only really works for our main group elements. So it doesn't explain the reactivity or behavior of the transition metals, and so we are going to restrict our exploration of Lewis theory to those elements for which it's operative, the ones that apply, right? And so when you're doing Lewis theory, you only look at the main group to the exclusion of the rest of the periodic table. And when you do, you can figure out how many dots will be in the Lewis structure by counting your way over and through the main group, with the exception of, the only exception to this, is helium. So I'm going to X this out here and write in helium right here, and you'll see why. Or actually, this arrow is going to go all the way down to neon. So if you're in the first column of the main group, you will have 1 electron in your Lewis dot structure. If you're in the second group column, you'll have 2, 3, third column you'll have 3, fourth column you'll have 4, fifth column you'll have 5, sixth column you'll have 6, seventh column you'll have 7, Eighth column, you'll have 8. All right. These are all right here. These are the number of electrons in the Lewis dot structure. For an atom. All right, you can determine the number of electrons for the Lewis dot structure of an atom based on its position in the main group. And just to finally kind of clarify why helium is right here, helium only has 2 electrons, so there's no way it would have 8 because helium only has 2. So that's why I bumped it over to this column and axed it out of that final column. All right? So that's where we're going to call it a day for a lecture. We'll continue our discussion with Lewis theory on Monday. And we'll start using it to construct our very first molecules to look at how atoms come together and form bonds, both ionic and covalent, to make molecules. So that'll be an exciting day. We've got office hours tonight. Hit me up if you got questions. If not,